Now, for today, I would love to introduce our speakers, Armin and Pouriya, for our webinar. So, Armin is the science and data lead here at CLIMAtlantic. Armin's work focuses on science and data initiatives at CLIMAtlantic, bridging research, academia, and practical adaptation. With over a decade of experience in climate change, his experience spans a wide range of climate-related issues. Armin also has a PhD in meteorology and a master's in environmental management. And Armin's passionate about helping individuals, communities, and organizations with the knowledge and tools to adapt to climate change. Our second speaker is Pouriya Jafarpur, who is a physical science officer at the Canadian Centre for Climate Services within the Environment and Canada Climate Change. In his role, Pouriya specializes in supporting the extraction, analysis, and application of climate data with a particular focus on the building sector. He provides guidance, and advisory services, helping Canadians understand and address the impacts of climate change on built infrastructure. So, welcome to you both, and thank you so much for joining us today. And I'll hand over the slides to Armin.
Thank you so much, Muntaka, and hello, everyone. So today we are going to give you okay, it's working. Today we are going to give you a brief introduction of climate science basics. Of course, in our first webinar, my colleague Alex Cadell briefly mentioned some of that. And today we are going to build upon that knowledge with the fact in mind that many of you might have missed the first one. So you don't need to worry because we'll try to cover everything. And then we will jump into what resources are available for you to download climate data. And of course, then I will hand it out to Pouriya to walk us through what's available for specifically construction sector. So as I've mentioned, for the start, with the climate science, and the goal is not to cover, of course, all aspects of climate science, but explain why climate data matters for construction decisions, specifically when we are planning to build a road, planning to build a drainage system, and construction coastal structures that are expected to last for decades in our region. But let's start with the difference between daily weather and long-term climate. A simple way to think about this is that weather tells us the story what to wear today, whether I need an umbrella to go out or not, while climate tells us what kind of clothes do we need to have in our closet for long term. So specifically for construction, the same idea applies. Weather affects day-to-day operations, whether it's a good day to operate or to do construction or not, but climate affects the conditions that buildings and structures need to be designed for their lifetime. If the climate changes and our design assumptions do not change with it, we risk building for conditions that no longer represent the future. So climate change is not just a future issue anymore. We all know that the climate is already changed globally and in Canada, and it's mainly driven by human-made effects, which we know as GHGs, or greenhouse gas emissions. For the construction sectors, this is very important because past climate conditions, as I mentioned, are becoming less and less reliable, especially for guiding us for long-term decisions. As we mentioned, Canada is also warming, like our planet, but unfortunately, Canada is warming twice faster than the global average, specifically and more intensely in northern regions, as you can see in the map. It's getting warmer much faster compared to other regions. These changes can bring important impacts, including heavier rainfalls, changing in winter conditions, more heat exposure during the summer, and increased coastal risks like sea level rise and coastal flooding. In Nova Scotia, this is especially relevant for drainage design, for building durability, for freezing sow impacts when the temperature goes below and above zero, for worker safety, and for coastal development and structure maintenance in coastal regions. So now let's shift to climate science and climate projections. Climate projections are a little bit different from daily weather forecasts, which we see on our phones. Climate projections are not just weather forecasts. They do not tell us exactly what will happen on a specific date in the future. Instead, they help us understand how long-term climate conditions can change under different possible futures. So climate projections are produced using climate models. These models represent the climate systems, including atmosphere, ocean, land surface, and ice. They help us estimate future changes in variables such as temperature, precipitation, sea level rise, and in some extreme situations. Specifically for construction sector, projections are useful because they help us think beyond historical records that we have and consider future conditions and what to expect in the future. We do not rely on just one model to represent climate projections. We use different models to represent the system which might be slightly different. So the results are not identical. That is why we use multi-model ensembles. An ensemble helps us to understand the range of possible future conditions. Looking at the median and percentile ranges gives us a better sense of uncertainty associated with these projections that may rely on a single model. This is important for construction because design decisions often need to account for risk. And with considering the amount of uncertainty, we can account for the right amount of risk that we would like to be exposed to in the future. For example, this slide specifically highlights that the future of climate data from climate models and how it usually looks with different ranges. The median range, which we usually use, can be very useful, but it's not the only value that matters. If you are designing, if a project does have higher risk, and if it's going to last for such a long time in, for example, a coastal region, it may be important to look at higher percentiles and the higher amount of risk that we will expose to, or even a higher warming scenario, depending on the decision being made and importance of that structure, building, or infrastructure that we are trying to design. As you can see in the picture, you can see the median here of these climate averages and the different percentile, in this case from 10th percentile to 19th percentile, which gives us a range. And with that range, we do have flexibility to decide how much risk we are willing to take for our structures that we are designing or building. In a simpler way, if you go to climatedata.ca, you can see it as this, which is of course much simpler and easier to interpret and use and understand. In a simple term, possible future for greenhouse consideration go into a climate model, and climate projection comes out as an output of our climate model. These projections then provide information about future temperatures, precipitation, and other climate variables which we discuss. The important point for future climate data is linked, the important point here is that this data is linked to assumptions about future emission and warming scenarios. Different emission scenarios represent different possible futures, of course. For construction, scenario choice should depend on the lifespan, the location, and the importance of that asset. For example, if you're designing a hospital or other important structures, it's really important to consider high amount of risk because not only the lifespan of that structure matters, but also a hospital is a very, very important building to be safe. For short-term or low-risk decisions, one approach may be enough. But for long-living infrastructure, coastal developments, or major public assets, or systems that where failure could cause severe disasters, like if you're designing a bridge, it's often useful to consider higher emission and warming scenarios. One important thing is also to consider the uncertainty and manage the uncertainty within the models that we see. Historically, we often rely heavily on the past weather observation to guide structure designs, which of course that makes sense when climate conditions were relatively stable. But now, if we aim only for past conditions, we may miss future targets, which our building is going to last in that future climate. For construction sector, this means historical data alone may underestimate future risks, especially for extreme rainfalls, extreme heat, coastal flooding, and changing winter conditions. And in addition to that, we are living in Atlantic Canada. We do have specific hazards to us, like Atlantic hurricane situations, which are getting worse in both intensity and the number of times that we are facing Atlantic hurricanes because of changing climate. Future projections, of course, do include uncertainty, but uncertainty does not mean that the information are not useful. It means we need to use the information appropriately. A more accurate approach for the future is for the future to be combined with the past observations and climate trends and model projections. And also, in addition to that, scenarios, and in top of all of that, as professionals, your own judgment for construction and coastal planning. This helps to support decisions that are more resilient for the future range that it's going to be changing. One of the great resources that you can always go to and everything on it is available for free and it covers the whole country is climatedata.ca. This is where users can access Canadian climate data, explore future projections, and find learning resources that explain how to use climate information in decision making. ClimateData.ca provides high-resolution future climate data on a approximately 6 by 10 kilometer grids. And in addition to the grids, you do have several options to use municipal regions, watersheds, or even now upload your own shapefile to download the data based on your shapefile. And in addition to all of these geographical distributions, it also provides information for multiple emission scenarios and more than 35 climate variables and historical climate observations. And on top of everything, it does have a learning zone section, which you can learn how to use and apply the information and data available on the platform. Specifically for construction sector, this can support questions such as, how might rainfall intensity change in the future for my location? Or how might heat exposure change for my specific location of interest? How might freeze-thaw cycle conditions shift? And how might sea level rise change in my coastal community? These are all very valuable information which you can get from climatedata.ca. These are some of the variables that are available on climatedata.ca, specifically for coastal and construction sector in Nova Scotia. Some of them could be more relevant. For example, IDF data, which represents short duration rainfall intensity, maximum days with significant amount of precipitation, wet days, as we mentioned, freeze-thaw cycle, or heating and cooling degree day. And in addition to that, variables like humidex, which is a combination of humidity and temperature, and sea level rise, and of course, vertical allowance, which Pouriya will walk you through those variables. For coastal ideas, sea level rise and vertical allowance are very useful. Uh, and as I mentioned, Pouriya will walk you through that. And the main takeaway is that climatedata.ca is not only for data, and it's not just a data portal. You can always find very valuable information specifically to learn how to use this data and how to apply this data. Now I pass it to Pouriya to walk you through what's available specifically on climatedata.ca for construction sector.
Thank you so much, Armin. I'll take control here. Yeah, so before I begin, my name is again Pouriya Jafarpur. I'm a climate scientist at Canadian Centre for Climate Services. Currently working from Toronto, the traditional territories of Main Nations, including the Mississaugas of the Credit, the Anishinaabeg, the Chippewa, and the Haudenosaunee, and the Wendat peoples. Perfect. And yeah, so we'll go before I start talking about the data available on climatedata.ca for buildings. I'll give a quick introduction to CCCS. So on who we are and what we do. So CCCS is a multidisciplinary team with expertise across a broad range of climate-related topics. And our mission is to provide Canadians with information and support them to consider climate change in the decision making. We have a support desk and a website that you can access and send us an email or ask us any question that you have in terms of finding the right data or a guidance question on what data to use, and we can always support you with that. In terms of what we do, so Canadian Centre for Climate Services provides access to climate data portals. So there are a number of different climate data portals available. One of them being climatedata.ca, as Armin mentioned. On climatedata.ca or other portals, you can find data to visualize using different tools. We have multiple apps available on climatedata.ca as well. And these are user-friendly online data sets, and they give you options to download the data or analyze the data if the data has different thresholds and you want to change those, or access the data for different kind of locations. You can upload shapefiles and download that, and you're not only limited to grid cells. In terms of guidance, we have a number of different learning content on climate science, as well as the data that's available on climatedata.ca. Again, we have the support desk. We have a training team that can help you with presentations. We do also have a number of different workshops and worksheets that can support that. And again, we all do provide guidance on data usage as well on climatedata.ca and support developing guidance reports as well. In terms of outreach, we do have an outreach team and engagement. So before any data is created, we try to talk to all the experts across Canada to get a better sense of where the data gaps are and where we can support that. What are the best practices in creating a data set in terms of future projections that might not be available. We have different social media channels and that you can follow us on. We have publication, blogs, and newsletters that go out every month on climatedata.ca. And again, as I mentioned, we do co-develop a number of different data sets on climatedata.ca, both working with external partners as well as internal ones. And then in terms of collaboration, we support a national network of regional climate organizations, CLIMAtlantic being one of them, to enhance localized data. And again, we work with researchers internally and externally in the federal government. And on this last point, in terms of collaboration, I just want to share this map of all the regional climate service providers. So we are the federal climate service providers, but we work with a number of different regional providers, including CLIMAtlantic for Atlantic Canada. So now moving on to the future climate data that's available for buildings. So as a general idea, there are two different compliance pathways for building code compliance, one being a prescriptive compliance, which you often see if you require an insulation value for different types of wall or roof types or window type. You can find what climate zones are you're in, and based on the temperature projection, or historically based on the temperature for that location, you would know exactly what kind of design value you would use when it comes to designing your infrastructure or buildings. And then the second one is a performance compliance pathway. And in that compliance pathway, you would design a model, you would design a building based on running a simulation for a reference building model, and then you compare that with your kind of design building and try to go above the requirements in terms of acceptable baseline for energy usage. So what we have done at CCCS is trying to provide future climate data projections to support these two compliance pathways. So climate zones and climatic design data for prescriptive pathway, and then future building weather files for the building simulation that comes as part of the performance compliance pathway. And we'll go over all these three data sets here. So the first one that I would like to kind of go over is the climate zone classifications for buildings. So the National Energy Code of Canada for buildings provides the minimum energy requirements for building design. Historically, climate zones were based on historical heating degree days. And as you see on the table to the right, NECB divides Canada into 6 different climate zones, going from 4 to 8, based on the heating degree days for a building location. So those are based on station data set. But again, as Armin mentioned in the opening, if we're designing a building that is going to last 50, 100 years into the future, the idea of designing that based on historical data sets no longer makes sense. And as a result, kind of CCCS had heating degree days projection. So we created a building climate zone specifically for building designers that will show you a glimpse of how the scale of climate change can impact the building design in the future. So on the right, you can see clearly how pretty much every climate zone will shift from current timelines to the end of the century. So the projections go up to 2100. And if you go on climatedata.ca and select some of the grid cells that comes with the map, you can kind of see that in some instances, heating degree days are going below the 3000 level. So there is going to be a need in the future as well to change the National Energy Code for buildings and maybe include additional climate zones that we didn't historically need because the heating degree days were higher than that. The next data sets that is currently available are weather files for building energy simulation. So this one kind of is relevant to the performance compliance pathway. There are 2 different data sets available for future weather files. One being developed by the Pacific Climate Impacts Consortium, PCIC, and then the second one, the National Research Council, NRC. The guidance and the differences between these 2 weather files are provided as part of the Learning Zone articles on climatedata.ca. So there is going to be a link in the chat that you can kind of view those. And maybe just a quick background of what building simulation is. So when you're designing a building, you would require, in general, two files as an input to the building simulation, one being a building file that includes all the information for your building. That is the type of occupancy, what type of building is it? Is it going to be a residential building, an office building? What type of HVAC system you're using? How many hours during a year is that building occupied? And then the second one is a weather file, which tells you what conditions the building is going to be operating under. So the idea is to create future weather files to run these simulations using those. Again, historically, weather files have been based on historical data sets, and there are studies which the results on the right side shows you how a simple change in the weather file input can have on energy consumption in the building, but also in terms of comfort level. So on the top, you can see a building simulation that was done for Toronto as well as Victoria. Same building file, so same building, a multi-unit residential building was simulated with two different weather files, one being a historical weather files, and then the second one being a future weather files. And the darker colors show you the cooling load and heating load, the historical cooling load and the historical heating load for the buildings for that residential building. And then using the same building and running that with a future weather file, you can clearly see how much of a change was simulated and was projected for that building. So a reduction in heating loads for both cities, obviously at different magnitudes, and then an increase in cooling loads for that building in the future is expected. So it's really important to, again, run your simulations using both historical and future weather files and select the right kind of weather file input, as those would have a significant impact on your design condition and your HVAC system. And then the second one, just touching base on comfort level, this one shows you an office building. So if you're looking from the top, this project kind of focused on dividing the top floor of the building into 5 different zones and running a simulation for that building using historical weather files, and then 3 different future weather files, kind of beginning of the century towards the end of the century, and then looking at the number of hours that a cooling set point was not met. So if you're designing an HVAC system based on historical data, that HVAC system might not be able to provide you the cooling set points that you will need under future climate conditions by the end of the century. We can see there is an increase in the number of hours that those zones will be becoming more uncomfortable in the future. Oh, I think I double clicked here. Yes, okay. And then the third data set is the design value summaries or design climatic design data that is now available as part of the National Building Code of Canada. So the building code was updated in December of last year. You can find NBC as part of the NRC's publication archive. And for the first time ever anywhere in the world, the Appendix C, Table C2 of the building code includes climatic design data based on future projections. And these future projections are based on a 2.5-degree global warming levels. And over the next slides, I will kind of go over what global warming levels mean. It's a little bit different from emission scenarios that go into that come out of the model projections, but they try to kind of simplified it for users, not having to really select different emission scenarios. And I will touch on what 2.5-degree global warming level means here. So The data that is now available as part of the building code was actually created by Environment and Climate Change Canada back in 2019. So since then, we've had this data available on climatedata.ca as part of the design value summaries variable. So the idea was to create a one-page, easy to use PDF files that could be easily pasted into drawings of records and specifications by designers, engineers, and architects, and to simplify kind of the back and forth between the different stakeholders when it comes to designing a building. And this design value summary is in addition to that the kind of table C2 values includes advisory guidance as well. As I mentioned, the building code is using the 2.5-degree global warming level projection. In the design value summaries, we decided to include 2 additional global warming levels, 1.5 and 3-degree global warming level projections, again, to give designers a range of numbers to improve accuracy and precision of the data that they're using for their design. So if you go to climatedata.ca and you click on station, this is the design value summaries that you will get. Again, it is very similar. So the data that comes in the table here is very similar. It's exactly what you will get as part of the table C2 of the building code. The only difference is here with the existing kind of data that's on climatedata.ca is that this is based on a global warming level. So there is no specific time horizon and there is no greenhouse gas emission scenarios. And global warming level is the average of global temperature increase from a baseline. And the baseline here is 1986 to 2016. And we've tried to include all this information in this one-page PDF summary so you can easily access that and understand it. And then again, we wanted to include a range of global warming levels. So in addition to the 2.5-degree global warming levels, we're providing the 1.5 and 3 degrees here. And the reason the building code is using the 2.5-degree global warming level is that when the building code decided to use projections back in 2020, and we often talk about, when we talk about buildings, we talk about kind of buildings having a 50-year design service life. So design service life at 50 years from 2020 ended up being in the range of 2070 period. And that is equivalent to the 2.5-degree level global warming level. So that's under RSP 8.5, 2.5 degrees, you can see the 2070. So this table is also available as part of kind of the methodology behind the climatic design value that was created. So if you're interested in not only global warming levels, but you're interested in going back and understanding emission scenarios and time periods, you can kind of go back and forth between the two concepts. Global warming level conversion to emission scenarios and time period here. And here I just quickly want to go over what you will see when you open up or download the design value summaries from the climatedata.ca. So at the top of the one-page PDF summaries, we have some information in terms of what the location is that you have selected, kind of the version of this. So in the future, if we update this design value summary PDF, you can easily keep track of it. The baseline period, which is really important, what baseline we're comparing the future projections to, as well as links to the methodology of behind the future projection data set. So as part of the CRB-CPI, the Climate Resilient Buildings and Core Public Infrastructure Report. So next we have the table. So again, this is exactly what you will see as part of the table C2 of the building code. The building code will only have a single line that is a combination of kind of future projection and historical. Here, to simplify it, we are showing you the historical values or what was previously in the National Building Code 2015 version. And then we have the 2 different global warming level projections, 1.5 degree and the 3 degree. projections, and then a number of different climatic design values that are available. And then in terms of levels of global warming, so again, we are looking at a reference of saying 2.5-degree global warming level increase relative to the 1986 to 2016. So if you want to know exactly how much 2.5-degree global warming is, that would be relevant to this time period. So again, if the baseline period changes, the global warming level can also change. And then you can also convert that to a pre-industrial baseline as well. So if your baseline is being compared to a pre-industrial level, then you would add the difference between the historical baseline to the pre-industrial baseline. So you can know exactly what global warming level data you receive. And in terms of why we selected the 1.5 and 3-degree, which is slightly different from the global warming level projection that's in the building code. Again, one was to provide additional data to support design, but also the 1.5-degree kind of aligns with a medium short-term design service life of components. So that is kind of like if you're designing something that has a 10 to 30-year design service life, like a HVAC plants or your fenestration, you can use those projections. And then the 3, which is past the 2.5-degree global warmings, and it's closer to the end of the century, so more of a long-term design service life for your components, again, 50 plus, and those could be your primary structure. So some of the design that maybe you don't have to kind of change them or look at them for the next 50 years, and it's more long-term. And then finally, there are some guidance notes here that help you use this data and kind of note how they are within the National Building Code, and explains the minimax approach, which the building code is using. So what the minimax approach is, for example, in the building code, it was decided that if any of the design variables, for example, snow load, decreases in the future because of climate change, then the value in the building code would remain as historical. Again, because we want to use the highest and the most stringent numbers. So we don't want to design a building currently that can't withstand snow loads, although those would decrease in the future. So the minimax approach means just using the most stringent number. Some of the variables, if it's decreasing in the future, then we'll be using the historical values. But then if they are increasing, then those numbers would show future projections. And then at the bottom, there are information for our support desk that you can kind of reach out if you have any questions, and links to learning zones as well. And then, yeah, I do kind of want to quickly touch base in the interest of time on 3 additional data sets, maybe not specifically for buildings, but also important for coastal infrastructure design. One being short duration rainfall, or the IDF data, so intensity, duration, frequency data, which is really important decision making about the risk of extreme precipitation, or if you're designing a drainage systems, and or you're predicting kind of flooding risk for your region. The IDF data is available on climatedata.ca. Again, station-based data sets. You can click on a station, you would get a number of different options for files. The data is available both in CMIP6 and CMIP5 projections, and there are guides that come along with the data sets explaining the future projection data sets, how they were created. Yeah, links as well to climatedata.ca's learning zone and support desk. So if you have any questions, you can reach out to. The IDF data set is based on a scaling method, and the scaling method is explained on climatedata.ca's learning zone. So if you're interested in that, you can check those out as well. And then the last 2 days data sets, relative sea level change, as well as the vertical allowance. So these are updated on climatedata.ca. The relative sea level change is the change in the ocean height relative to a coastline. and it's really valuable in understanding the risk of coastal flooding that could impact local infrastructure. There is going to be a link in the chat as well that will send you to a learning zone that kind of explains the relative sea level change. And yeah, here's in this image just showing what this means. The relative sea level, again, is a comparison of the mean water level at present compared to how that relative sea level will change in the future, minus the changes in the terrestrial elevation of the present day, and that could change based on uh, subsidence of the Earth crust or the uplift that could happen as the result of glacier and ice sheet melting in the north. Mostly for Atlantic Canada, there is going to be a subsidence of the Earth, an increase in the relative sea level change by kind of mid-century towards the end of the century. In terms of vertical allowance, so the vertical allowance data is the projection that shows you the amount by which an asset, whether that's a building or a bridge or piers, could be raised under sea level rise in the future. Without kind of experiencing any of the frequency of the coastal flooding in that future period. So the vertical allowance includes storm surge and tides in its projections. And that is kind of, yes, relative to including the relative sea level change on top of storm surge and tides. And that tells you how much relative to the coastal regions you will need to kind of increase your height of your assets in order not to face any floodings in the future. And again, the link in the chat will include the Learning Zone article, which explains this in more detail and describes the methodology and limitations of the data sets. The data sets does not go above, I think, 70 north latitude, just because there is no data in terms of storm surge projections, but there should be data sets available for Atlantic Canada. And I think that's it. Thank you so much.
Thank you so much, Armin and Pouriya, for your presentation today. It was super informative and a great intro to all the resources available, as well as an intro to climate data and CCCS. So if anyone's interested in reaching out to Pouriya or CCCS, the contact information is on the screen here. Okay, so we can dive right into the Q&A session for the rest of our presentation. So for those who have any questions, you can put them in the Q&A chat box below, or you can raise your hand as well if you'd like. So I'll give it a few seconds for folks to write in their questions. And I guess while we wait, I do have a question. So a lot of different data and climate variables and data sets were shared today. Are there any other upcoming data sets that we should keep our eyes out, especially for the construction sector?
Yeah, that's a great question. So we're always working on data sets. Some will take longer to be developed, and we want to make sure they are valuable to the users. I think the next data set that will be coming over the next month or so on climatedata.ca would be the snowfall projections for all Canada. And the snowfall will divide the snowfall amount and the kind of the water precipitation to different projections. Previously, they were combined together or they were projected just during the winter period, but now we have the ability to separate those. So snowfall projections would be the next data sets on climatedata.ca. Another one that we're actively working on is sea surface temperature, SST. I don't have an exact timeline on when that will be available, but we're hoping over the next year to have that completed and tested and available on climatedata.ca as well. Last year, we released fire weather projections that I did not touch here, go over. But we released fire weather projection, which includes how dry and how windy and how hot conditions are going to be across Canada, and they can be used for kind of looking at fire risks across Canada. So that is available as a application. If you go to climatedata.ca, we have a tab that's called apps, and you can find that there. I think yeah, those are it for now. But yeah, if there is a data set that I didn't mention here or you want to know more about, you can always reach out to CLIMAtlantic or CCCS or myself.
Thank you. That was super exciting. The next question I have is, so we did have a webinar on building codes, but I would love to hear your response on when does the building code need to be adopted?
Yeah, so again, the building code was released in December. I believe the provinces and territories have 15 to 18 months to either adopt the building code or create their own that is using the building code as a minimum required. They can go beyond that. So again, over the next year or so, the that needs to be adopted by the provinces and territories. And again, CCS CLIMAtlantic is always here to support any questions that you might have. If you're a policy maker and you're deciding on what is the right global warming levels to select or what are the climate projections mean in the building code, you can always reach out to support.
Yes, totally. And Armin is part of the CLIMAtlantic team as well. So yeah, we're reachable. The next question I have, and it will be the last question. What are the biggest differences between the design value summaries between PKIC and climatedata.ca?
Yes. So the presentation when I was discussing the design value summaries, the PDF file that you get, there are links to the design value explorer, the DVE, which is created by PKIC. The Pacific Climate Impacts Consortium, which is a regional climate service provider in BC and Yukon. They use the data set that is in the building code, but the building code is based on station data. So what the data that's available as part of DVE is includes interpolated data set. So they try to fill the gaps between stations. So if your building is not close to a station, or if you're looking for the climatic design values that are in the building code or in the design value summaries that are shared here, but you don't want to go to a station that's far from your building or what you're designing, you can go to the DVE and you can find kind of grid cell uh, projections for any of the climatic design variables that are available there. So it kind of fills the gap, and there is data available for all Canada, not only station data, but the data behind the scene is all the same.
Thank you. So it looks like we have one question here in the chat from Evan. So Evan asked, what challenges do you think hinder the widespread adoption of these data sets among industry professionals?
Yeah, that's a great question. I think yeah, as Armin mentioned, the uncertainty that comes with future climate projection, there's still a bit of hesitation in terms of kind of how much we can rely on future projections when we have historical data sets that we have experience and they come from a recorded station data that we can just use. But as we saw, the climate has already changed and it will even change further in future, and we can't really just rely on historical data sets or trends of historical data sets. The climate system is chaotic, and we try providing projections for those as best as we can. And that's the idea of like having multiple values, multiple emission scenarios, multiple model projections. I think there is a bit of kind of difficulty of not only relying on one single data set and using multiple projections to design. Again, it's hard to know what the future is going to be, and then having to use multiple data sets and projections will add to the cost of the design. You have to like simulate more building simulations with like a multiple future scenarios. So that will add to the kind of initial cost of a design, but long term, they will have a better impact for all Canadians and build resilience for our infrastructure. So the difficulty, I think, is the kind of one is the cost. Second is the time that is required to run multiple scenarios and multiple model data sets that are available for future.
Yeah, and for myself to add to Pouriya's point, this is a very good question. One of the challenges that I hear from practitioners is that they usually can find access to data sets, but the challenge for them is to which data set to use for their exact decision. And that's why on climatedata.ca, the learning zone section is very valuable resource for them to go through to see what existing data sets can help them for their decision making. For example, do they need IDF curves information? Do they need a sea level rise projection? And the other challenge that I've seen that many professionals came across is the issue for some of them for local decision making. So for professionals often want a highly site-specific answers, while many climate data sets do have regional capability, but the exact site-specific analysis usually needs a little bit of local expertise and engineering judgments. That's why we always recommend, in addition to all the data and information, it's very important that there is a region-specific local analysis for using the data.
Totally. Thank you both for answering the questions. I think that's the last one here, so I will move on. I'll move on with wrap up. So first of all, I wanted to thank you both, Armin and Pouriya, for being here and presenting for us, as well as our attendees for attending today.